Welcome to RhinoCFD Basics. In this video we'll explain how you can tell if your solution is converged and provide some tips on how best to get a converged solution. A CFD simulation involves solving conservation equations for variables such as mass, momentum, and energy. However, these equations are highly nonlinear, and as a result have to be solved by an iterative procedure. The idea is that after a certain number of iterations, depending on the complexity of the simulation, the process will converge to a solution in which all the equations are satisfied with minimal error. The easiest and recommended method, especially for those new to CFD, is to use the graphs produced while the simulation is running. The chart on the left shows the values of each variable at the location in the domain where the probe is located. This should be placed somewhere where the flow is interesting, and definitely not inside a solid. In general, when these lines flatten out, it means that the values in the variables are stable, which is one indicator of convergence. The plot on the right-hand side is the sum of residuals, and can be thought of as the sum of errors for each of the equations being solved. In general, if these lines tend to move downwards towards the bottom of the graph, the simulation is converging. The percentage error indicated below the graph quantifies this error. There is no value that guarantees convergence, but in general you should aim for percentage error values for mass and temperature, P1 and Tem1, of less than 0.1%, and for momentum, U1, V1, and W1, of less than 5%. Alternative convergence plots can be selected, namely the maximum absolute correction of each variable in the domain, which ideally should be close to 0, and the maximum and minimum values for each variable in the domain, which should be stable values. Establishing convergence is not always straightforward, and care should be taken before blindly trusting any of the results produced. Further information about the results produced by the simulation and its level of convergence can be found in the result file, accessible from the toolbar or from your working directory. In it, you'll find quantitative information regarding the residual errors, and most importantly, net source information, which lists the inflow or outflow rate of each variable at each relevant object, and adds these to give the net sums, which should be 0 if the solution is perfectly converged. It is good practice to check these net sums for mass, R1, and temperature, Tem1, as well as for any variables representing pollutants or smoke. The net sums should be several orders of magnitude smaller than the individually itemized flow rates. To get any CFD simulation to converge, it is necessary to employ a technique known as relaxation. Relaxation essentially damps oscillation of variable values from iteration to iteration. It is akin to damping in control theory. Each variable has a relaxation parameter that can be set by the user, which controls the strength of the damping. Note that a small value for the parameter gives a heavy damping, and vice versa. When you set up a model in RhinoCFD, an automatic convergence tool known as converged is employed. This takes care of everything, so that the user does not need to bother with setting relaxation parameters. However, the automatic tool is sometimes over-conservative, leading to runtimes which are longer than they should be. Some experimenting with manually set relaxation can therefore pay dividends. To do this, enter the main menu, click on Numerics, and then on Relaxation Control. Automatic Convergence Control should be switched off. You will then see that each variable has a relax method, linear or false DT, and a value. Describing this in detail is a complex topic, so here we will just touch on the basics. You will see that the pressure P1 is set to linear with a value of 1. This should not be changed. The velocities U1, V1, and W1 should be set to false DT, and the value, i.e. the relaxation parameter, should be set to typical characteristic time for the flow in seconds. Often a suitable value may be found by estimating how long the flow might take to flow through a single cell in the region where the mesh is fairly fine. In other words, take a typical flow velocity in meters per second and divide it by the width of one of the smaller cells in meters. Use the same number for all three velocity settings. For temperature, if there are thermally conducting solids present, use linear with a value of perhaps 0.3. If there are no conducting solids, you can do the same, or use false DT with the same numerical values as for the velocities. If the right-hand curve shoots upwards and you see high values for the percentage error, the run is likely diverging. Sometimes you may see NaN, not a number. This definitely means divergence. You need to try the run again with harder relaxation, which means using smaller relaxation parameters. Thanks for watching this RhinoCFD Basics tutorial. For more information, visit rhinocfd.com.